Hello and welcome to the 5.7 notes. This is a section of notes over what's called the trapezoidal rule. But if you're a fan of Star Wars and you are familiar with the line that General Akbar says, how it's a trap, then I often like to think of this as it's a trapezoidal rule, okay? So, what we've been using is rectangles, and one thing that we can use is a trapezoid. So I kind of want to just go through and talk about some of the geometry associated with the area of a trapezoid. So if I draw a trapezoid that we would see here, then you'd see something like this, okay? A four-sided figure like that, I'm going to call this the height. I'm going to call this base sub 1, and this is base sub 2, okay? And so we can calculate the area of this by taking the height, dividing it by 2, and multiplying it by the sum of b sub 1 plus b sub 2. Okay, you have this one, or you can write it like this. You can say that the area of this trapezoid is h, your height, times the sum of your bases, all divided by 2. Either way, you get the same thing, and I'll primarily be using this one. It's a little bit easier to see, and you'll kind of see why I'm going to use this one later on. But let's kind of translate this over to what we're going to need this for. When we draw our trapezoids, usually we draw them like this, okay? Where they've kind of been rotated. So what I want you to see here is that, right here is where your height is. Well, that distance here is your height, but because we're dealing with a horizontal distance, we're going to call this length here delta x, okay? So I'm going to call this delta x, okay? And then these are just function values. The heights are just these different y values. So I'm going to call this, say, y sub 1 and y sub 2, okay? Meaning my first y value and my second y value, okay? So then, if I were to use that same area formula, okay, then I would say this, that the area of this trapezoid is equal to delta x, my height, okay, I'm using this, height over 2. My height was delta x, so I'm going to say delta x over 2, and then times the sum of my bases. Well, our bases are now the y values of the function, so I'm just going to say that this is y sub 1 plus y sub 2, okay? So this is going to be what we're going to want to do here. And so let's go ahead and apply all of this to this example that we've kind of done before with the graph 1 over x. And so if I'm going to do the trapezoid rule, the first thing I want to do is calculate delta x. So step 1, calculate delta x, and that's going to be 5 minus 1 over 4 trapezoids. And that's going to be 4 over 4, which is 1, so delta x is equal to 1. So I'm going to partition this off from 1 to 5, okay, with a distance of 1. Okay, that's my delta x. And I'm going to use all my y values on this. Okay, typically when we use like LRAM or RRAM, we wouldn't use all the y values. But on the trapezoid rule, we are going to use all the y values. So I'm going to just draw lines that go straight up to my functions and plot those points. Okay, and draw those straight up, draw this straight up, and draw this straight up. Okay. And so now what I want to do is I'm going to draw this over to the side, over here, 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 and then I'm going to connect my y values with a line, okay? And we end up getting a pretty decent approximation from this. It seems to fit this pretty well, but we still actually get a better approximation by doing MRAM, but this is just another tool that we have, okay? So I'm going to come in here and I'm going to label all of these trapezoids. First, I'm going to call this delta x is equal to 1, delta x equals 1, delta x equals 1, and then delta x is equal to 1. Okay? So then what I want to do is, and I need to find all the different heights here. Okay, I'm going to call this f of 1. Okay, I'm going to call this height f of 2. I'm going to call this height f of 3, this f of 4, and then this last one is f of 5. Okay, and I'm going to go ahead and just label out my heights. 1/5, this is a 4th, this is a 3rd, this is a 1/2, and the last one is just 1. Okay, so now I want to find the area of each of these trapezoids and add them together. Okay, and what you'll notice is that we'll have a pattern here. But let's think about this. Think about what we're trying to do. Okay, our goal is to approximate the integral from 1 to 5 of 1 over x dx. Okay. And so what I want to do is start to add up all of these trapezoids. Okay, now here's what I'm going to do. All right, I'm going to kind of write that stuff down here. I'm going to write that the area here, is equal to, and remember we want to do delta x, the height of this rectangle, divided by 2, times my function values, okay, the sum of my function values. So watch what I do. I'm going to do delta x over 2 times f of 1 plus f of 2, okay? And I'm going to take my area of this trapezoid, okay? And so this area is equal to delta x over 2 times the sum of my function values. Now my function value here is f of 2 and f of 3, okay? So I get f of 2 plus f of 3, all right? The area on this one, the area is equal to delta x over 2 times the quantity. All right, for that one, I've got this height, which is f of 3, and this height, which is f of 4. So I'm going to write f of 3 plus f of 4. Okay, and then the last one that I've got, the area for this, is delta x over 2 times f of 4 plus f of 5. Okay? And the reason why I wrote all those out, I want to show you that I have all of those separate before I just went ahead and started writing. But now I just want to add all of these up. Okay, so now here's what I want to do. Okay, and I'm going to do use a little bit of notation here. But I'm going to come in here and say that this is just, okay, I've got delta x over 2 times f of 1 plus f of 2. Plus, okay, the area of the next one, which was delta x over 2 times f of 2 plus f of 3, okay, and then plus delta x over 2 times f of 3 plus f of 4, okay. And then the last one is plus delta x over 2 times f of 4 plus f of 5. Okay, so now you have all this written out. Each of these are the area of each of those trapezoids. Okay, and what I want to do is kind of see what we can do here. Because if I were to just plug in my numbers now, that's so much computation. And I kind of see a few patterns here, so let's kind of identify what those patterns are to try and make this as easy as possible. So, let's go ahead and here I'm going to write the integral from 1 to 5 of 1 over x dx, and that's going to be approximately, all right, now let's see what I can do here. Now, each of these has a common delta x over 2. So what I can do is I can factor out a common delta x over 2 out of each of those. And that just leaves me with the sum of all of these y values. Okay, so if I go in there and I do that, let me factor out a delta x over 2. And let's think about what we're left with. We're left with f of 1 plus f of 2. okay, the sum of these two y values. Okay, and then we have f of 2 plus f of 3. So plus f of 2 plus f of 3. Okay, and then we have f of 3 plus f of 4. So plus f of 3 plus f of 4. Okay, and then we've got f of 4 plus f of 5. So plus f of 4 plus f of 5. Okay, and that's it. Okay, that's what we can do, but we can still simplify this a little bit even further. Okay, and what I notice is that I only have one y value evaluated at x equals 1. I have one f of 1. And I only have one f of 5. So my first and last y values, I only add them once. But what I see here is that all the other interior y values are being added twice. So let's simplify this even further. Okay, let me come in here and say that the integral from 1 to 5 of 1 over x dx is approximately equal to delta x over 2 times f of 1 plus, and I want you to see here that I have two of these f of 2s. So I'm going to do 2 times f of 2, okay, plus, again, I have two f of 3s. So I'm going to do 2 times f of 3, and then I have two f of 4s, okay, and so plus 2 times f of 4, and then I just have a single f of 5, so plus f of 5. Okay, so now, all right, I have this nice easy formula that I can do, and now is when I want to actually plug in my numbers, okay? And guys, I'm not going to expect you to do this every time. You can kind of, if you know what you're doing with the trapezoid rule, I would want you to automatically skip to this step, okay? And we're going to write a rule for this. So, but what I've got, okay, let's go ahead and plug in our numbers. And so the integral from 1 to 5 of 1 over x dx is approximately equal to, delta x was 1, so 1/2 times 1 plus 2 times f of 2, which was 1/2, okay? And then plus 2 times f of 3, which was 1/3, all right, plus, and then 2 times f of 4, so that's 1/4, and then plus a single f of 5, and that's just 1/5, okay? All right, so now we just want to evaluate this, and so we end up getting the integral from 1 to 5 of 1 over x dx is approximately equal to 1/2. All right, let's go ahead and simplify this as much as we can. This is going to give me 1 plus 1 plus 2/3 plus 2 times 1/4 is 1/2, and then plus 1/5. Okay, and I'm just going to quickly compute this in the calculator. Give me a second here. So the approximation that we get is the integral from 1 to 5 of 1 over x dx is approximately equal to, and after I added up all these numbers and multiplied by 1/2, I ended up getting a value of 1.683, which is pretty close to what we're supposed to get. But again, guys, this is just, another approximation. Okay, it's approximation, and remember that this part right here is exact. This is the exact area. This is the approximation of the area. Okay? And so, I went through that problem like that so that you could kind of see what I'm going to do. I'm going to do another video and show you that the same kind of rule applies for the trapezoidal rule. So we'll just do a generic one just like that. So I'm going to go ahead and stop this, and we'll do another video. Thank you. Bye.